Welcome back. In the last video, we discussed about the basics of code optimization. Today, we are going to talk about the different techniques to achieve the optimization. These techniques can be applied both before and during the target code generation. Typically, the machine independent optimizations are performed before the target code is generated, that is, after the intermediate code generation phase. And the machine dependent optimizations are performed along with the target code generation. A general working strategy of these techniques is that they try to detect certain patterns in the program and then transform the code by replacing those patterns with equivalent but more efficient constructs. This statement will become more clear as we proceed further, as we discuss examples. The transformations done on the program can be local or global. Local transformations are performed by looking only at the statements in a basic block. That is, the optimizations are performed locally within the block, whereas the global transformations consider the entire code for doing the optimization. Generally, global transformations are performed only after the local transformations. The various optimization techniques can be divided into two major classes. One is known as function preserving transformations and the other one is loop optimizations. The function preserving transformations improve a program without changing the function it computes. The program might have been written to achieve some functionality. It might be computing some function. It should not happen that after the optimization you end up with the code showing some unexpected wrong results or throwing some errors which did not happen with the original unoptimized version. The functionality of the code should be preserved. That is what this statement means. This category is also known as semantics preserving transformation because the optimization techniques in this category preserve the semantics or the meaning of the program. Examples include common sub-expression elimination, copy propagation, dead code elimination, and constant fold. The second category is known as loop optimizations, which has to do something with the loops in a program. There is a well accepted phenomenon known as 90-10 rule. It states that 90% of the time is spent in executing 10% of the code. You know that the loops form only a small portion of the code, but even then the programs spend their bulk of time executing the loops. Especially the inner loops are the most heavily traveled parts of a program. So this means you can achieve a great deal of optimization if you concentrate on the inner loops. The execution time of a program can be improved by decreasing the length of the inner loop, that is, by reducing the number of instructions in the inner loop. Sometimes this might result in adding more number of instructions to the outside of the loop, but we don't bother about that if the overall execution time is improved. Under the category of loop optimizations, we have three techniques. One is code motion, second one is reduction in strength, and the final one is induction variable elimination. In this lecture, we will concentrate on the function preserving transformations and we will take up the loop optimizations in the next video. So we will begin with the first example of function preserving transformation, that is common sub-expression elimination. Often you might have seen repeated calculations of the same value in a program. That is, there will be two or more statements that compute the same value. Those statements are known as common sub-expressions. It could be defined technically like this. An occurrence of an expression E is called a common sub-expression if E was previously computed and the values of the variables in E have not changed since the previous computation. Since the value of the variables in the expression have not changed, you can reuse the previously computed value. That is, you can avoid the recomputations. That is the essence of common sub-expression elimination. You try to eliminate all the computations but just retain the original or the first computation of the expression's value. All the subsequent computations can be removed from the program. Common subexpression elimination is of two types. One is local and the other one is global. We will first discuss the local case, then we will move to the global case. This flow graph will be used for our discussions throughout. This will serve as an running example. For discussing the local common subexpression elimination, let us concentrate on the block B5. So if you look at the block B5, you find that T6 and T7 both compute the same expression 4 star I. Similarly, T8 and T10 both compute the same expression 4 star j. That means you have common sub-expressions here. You can eliminate them. So the idea is to use T6 instead of T7 and T8 instead of T10. That is what we are going to do now. You eliminate T7. At places of T7 you can use T6. This is going to become A of T6 equal to T9. Similarly, you eliminate T10 and at its places you can use T8. So this statement can be written as A of T8 equal to X. This is the result of applying the local common subexpression elimination to the block B5. Now proceeding to the global optimization. Here you have two expressions 4 star I and 4 star j. Let us see. These are still common sub-expressions if you consider the entire flow graph. Let us move back to the flow graph. Here in block B3 you find that 4 star j is already computed. That means 4 star j is common sub-expression. In block B3, T4 is holding the value of 4 star j. In the previous code, this T8 can be now replaced with T4. Let us do that. You remove the variable T8 and use T4 in its place. This statement is going to become D9 equal to A of T4 and this will be written as A of T4 equal to X. Now if you concentrate on these two statements, you find that after these statements are executed, A of T6 is going to get the value of A of T4. Why this is true? Because the first statement assigns the value of A of T4 to T9, the second statement assigns T9 to A of T6. So in essence, A of T6 is getting the value of A of T4. These two statements can now be replaced as A of T6 equal to A of T4. There is one more optimization that we can achieve here. Let me show what that is. Here in block B3 you find that T5 is here holding the value of A of T4. So what you can do there is these two statements can be replaced by the single statement A of T6 equal to A of T4, but A of T4 is contained in the variable T5, so you can write as A of T6 equal to T5. A of T6 equal to T5. So I have finished the processing of the expression 4 star j. There is one more expression 4 star I. Let us see if that is also a common sub-expression. Let me take you to the flow graph. In block 2 you find that 4 star I is already computed by the variable T2. So you can replace T6 with T2. So remove T6 and use T2 in its place. This statement will be written as X equal to A of T2 and this will become A of T2 equal to T5. There is one final optimization that we can do here, that is in block B2 you find that A of T2 is held in the variable T3. So instead of a of t2 there, you can use t3. Do that also. X equal to a of t2 was the previous statement, that is now written as x equal to t3. So this is the end result of applying the global common sub-expression elimination to block B5 by considering the entire flow graph. A similar sequence of transformations can be applied to block B6 also. Doing so, we will be able to transform the flow graph as follows. This is the final flow graph after performing the common sub-expression elimination for both blocks B5 and B6. If you compare this figure with the original flow graph, you will find that in this optimized version, lot number of instructions have been eliminated from the blocks B5 and from block B6. Let us move on. The next example of optimization technique that we will discuss is copy propagation. To know what copy propagation is, you should understand what are copies. Let us define what a copy is. Assignments of the form A equal to B are called copy statements, or in short we call them as copies. The idea behind copy propagation is to substitute B for A whenever possible after the copy statement A equal to B. That is, this means that once you see the copy statement A equal to B, subsequent this statement, what you can do is at places of A you can just use B, that is you substitute B for A. That is the idea of copy propagation. Let me illustrate with an example. Let me take you back to the figure. In block B5 you have a copy statement. The first statement itself is a copy, x equal to t3. This is of the form A equal to B. So what is the idea behind copy propagation? You substitute B for A. So here you have A of t4 equal to x. A of t4 is equal to x. So that means what? This x can be replaced with t3. Similarly, in block B6 also you have a copy statement x equal to t3, and hence this statement A of t1 equal to x can be written as A of t1 equal to t3. This shows the copy propagation applied to the block B5, and this shows the result of applying copy propagation to block B6. The next technique that we will discuss is dead code elimination. As the name indicates, you try to eliminate dead code. So obviously the question will be, what do you mean by a dead code? Dead code is also known as useless code. It is a set of statements which compute values that never get used. So you have a collection of statements that compute values, but those values are used nowhere in the program. This implies that there is no point in computing those values. That is, you can eliminate the computations. You can eliminate the statements that compute the values. This is the idea behind dead code elimination. The dead code can be identified and the dead code can be eliminated. Let us take an example. Here you have a code. Assume there is a boolean variable by the name debug. So it can take one of the two possible values, true or false. Assume you have the assignment statement debug equal to false. Further down you have an if statement that uses the value of the boolean variable debug. If debug, print hello. If you apply copy propagation, what will happen is this debug will be replaced by false. So that means the condition of this statement will be evaluated to false. This implies the print statement will not be executed. In a sense, it will become a dead code, and hence that can be removed from the program. So if the print statement becomes dead code, there is no point in testing the condition also. The if statement will also become a dead code. That can also be eliminated. So the end result is that both the if statement and the print statement can be removed as they are dead code. Related to this dead code, we have the concept of live variables and dead variables. Let us see what they are. A variable is live at a point in a program if its value can be used subsequently. Otherwise, it is dead at that particular point. Suppose you have a variable y in a program. If its value is used subsequently, then we say that y is a live variable. But if the value of the variable y is not used subsequently, then y is said to be a dead variable. It is not used subsequently, it is dead. So as you might guess, the dead variables can be removed from the code because they serve no purpose. Let me give an example. So remember, this pertains to the block B5 and this pertains to the block B6 of the flow graph that we have been seeing. Here in both these blocks, x is a dead variable because in both of these blocks, although we are defining x like this, x is not used subsequently. So x is a dead variable in both cases, and we can remove the assignment statement. We can remove the statement x equal to t3. You can eliminate the dead variable x. This is our flow graph with the dead code elimination and copy propagation being applied. Block B5 and B6 have still been optimized. The last example in the category of function preserving transformations is constant folding. What do you mean by constant folding? Constant folding is the process of replacing expressions by the value. The value can be computed at the compile time. Let us see what this means. Suppose the compiler sees an expression in the statement in the program. It identifies that the expression's value is a constant. That is, it identifies that the expression evaluates to a constant value. So what the compiler can decide is, instead of postponing the evaluation of the expression to the runtime, it can evaluate the expression during compile time itself and then replace the expression with the evaluated value. This is idea behind constant folding. So constant folding is reducing that an expression's value is a constant and then replacing the expression by the evaluated constant value. That is constant folding. Let me give an example. Here you have a variable size which is assigned the value 100, and later on you have a variable t which is assigned the value of an expression that involves the variable size. So t equal to size minus 1. If size equal to 100, then size minus 1 will be evaluated to 99. So t can be assigned the value 99 as shown here. Similarly, in the if statement you have a condition that involves the variable t, I less than or equal to t. What you can do there is, instead of I less than or equal to t, you can just write I less than or equal to 99. Now you might ask why this is an optimization, because here you have the condition as I less than or equal to t. Here the condition is I less than or equal to 99. It almost looks similar, right? So what is optimization here? Thinking deep, we will find that here you are comparing I with the value of a variable. So you need to go to the memory and fetch the value of t. But here you don't need that because you are comparing I with the constant value. So this will be much more faster when you compare with this particular version. So that's all for now. In the next video we will discuss about the various loop optimization techniques. We will discuss about code motion, reduction in strength, and induction variable elimination. Thank you.